This week we're going to look at some more exponents, rational exponents in particular, and how that leads to some more word problems. So last week we saw that there's some laws of exponents. We saw that powers with the same base can be easily multiplied and divided. We keep the base, we add the exponents when we're multiplying powers with the same base. And when we're dividing power with the same base, we keep the base, subtract the exponents. We also saw that we can raise a power to an exponent. In that case, we keep the base and we multiply the exponents. We saw that we had negative exponents, where we flip the base and keep the positive exponent. We also have zero exponents. And we saw that we can solve exponential equations if we can get common bases. So here we have 4 to the 2x equals 8 cubed. We can get a common base there between 4 and 8. That's a base of 2. And then we have powers of powers, where we keep the base and multiply the exponents. And since we have a base of 2 in each case, the exponents must be equal. So 4x must equal 9, and then 4x equals 9 over 4. So let's take a look at a rational exponent. A rational number is a fraction, or is a number that can be expressed as a fraction a over b. And they have special meaning when we get into them as exponents. So let's take a look at an example here. Very straightforward one. Solve for x squared equals 25. We know what the answer is here. We know that we undo the exponent by taking the square root of both sides. And that leaves us with x equals plus minus 5. But what you notice here is that the exponent really is a 1. Now we never write that, but that's technically what it is. So the question becomes, what is this square root? And what we see is that the square root undid the exponent, and therefore it must be an exponent itself. In fact, it's an exponent that will give us this exponent of 1 that we have. So really we can solve the equation like this. We could take x squared equals 25. We could raise both sides to an exponent. Now I don't know what that exponent is, but that exponent will be the exact same as the square root. So I'll say x squared to the something would equal 25 to that same something. Here I put a question mark. I could have put m. I could have put p or some letter. Okay, so now the question becomes, what is this exponent? This exponent would be the square root. And so we know that we have to end up with an exponent of 1. We want all of this exponent to be a 1. Since we have the power of power, these two will multiply to give us 1. So now I know that, now I know that 2 to the something, or sorry, 2 times something equals 1. Well, that something is 1/2. And so what we see here is that if I raise both sides to the 1/2, then I get x by itself. I have effectively undone the exponent of 2, because when I multiply these together, top by top and bottom by bottom, I'll get x to the 1. So it's really important here to recognize that the square root is actually an exponent of 1/2. You can see there's the x to the 1. So we now recognize the square root as an exponent, a very particular exponent of 1/2. That is a rational exponent. It's a fraction. So what's an exponent of 1/3 mean? Well, let's take a look at an example here. Solve this for x. 8 to the 1/3 equals x. Well, what we see here is that we can cube both sides. And cubing both sides would give me a power of power. So I keep the base and multiply those exponents. It's going to give me 8 on the left-hand side and x cubed. Well, I know what this answer is. I know that this is x equals 2. So really what's happening here, is that we're looking at the cubed root when we look at an exponent of 1/3. And this asks, what to the 3 gives me 8? And the answer is 2. And so x equals 2. So the square root is the exponent of 1/2, and the cube root, which actually looks like this, 3 is inside there. Cube root is of x, let's say, is equal to x to the 1/3. And that asks what cubed gives you this answer of x. So we can take a look at some. We have 64 to the 1/6. Now again, that would mean what to the 6 gives us 64. Well, we know that answer. That's just 2. Note that it's not 2 to the 6. That's not the question is asking. It's asking what to the 6 gives us 64. And that answer is just 2. Here we have 81 to the 1/4. That asks what to the 4 gives us 81. That's just 3. This asks what cubed gives you 125. We know that answer is 5. There's no work to be shown here. We're just understanding what the question is asking. And all this started with this square root idea. And so we can represent all of these rational exponents with radical signs, root signs. Okay, for instance, the 5th root of 49, I have no idea what that is, but that can be written as 49 to the 1/5. And the cube root of 64, which we do know, that's 4. But it can also be written as 64 to the 1/3. And the 4th root of 10 can be written as, or sorry, the 4th root of 100 can be written as 100 to the 1/4. And now if you look at these bases, they're all perfect squares, so we can write them as such. And so what happens here is that now we have a power of power in each case. All of these can be simplified. So I can write 7 squared to the 1/5 is 7 to the 2/3. And 8 squared to the 1/3, I can write it as 8 to the 2/3. And 10 to the 2 to the 1/4 simplifies to 10 to the 1/2. And so what we see here is now we have rational exponents where the numerator isn't necessarily a 1. It can be, but it's not necessarily a 1. So here's an example where we want to evaluate. We should say without the calculator. And so what we have here is we see we have a rational exponent. I'm going to suggest that when we have a rational exponent, we rip the exponent apart. What I mean by that is we can write this as 25 squared to the 1/3. So when I rip this exponent apart, basically I'm taking a 2 off, and what's left is the 1. And so I have 125 squared, but I'm not sure I'm supposed to know that. So I could also write this as 125 to the 1/3 then squared. And that's because I said these are both powers of powers, and it doesn't matter which way I multiply. 2 times 1/3, 1/3 times 2, it gives me the original 2/3. So it doesn't matter which way I look at this, except for the fact that if I look at it 125 to the 1/3 squared, I know what 125 to the 1/3 is. That asks what cubed gives you 125, and the answer is 5. And so this all becomes 5 squared, which is 25. So 125 to the 2/3 equals 25. Here's another example. 9/4 to the 3/2. What happens here is, again, we rip the exponent apart. I can write this as 9/4 cubed to the 1/2, or as 9/4 to the 1/2 cubed. And I will know what the exponent of 1/2 is. That's just the square root. So the square root of 9 is 3. The square root of 4 is 2. And so what we'll do is we'll write those. There's 3 over 2, and then all that's cubed, so the answer is 27 over 8. So I'll give you a chance to work on these before we'll pause the video here before you look at the answers. So here I have 4 to the 5 over 2. Well, I can rip that apart. 4 to the 1/2. The 1/2 is the same as exponent, or sorry, it's the same as the square root. So this is all just a 2. 2 to the 5 is 32. Question B says 81 to the negative 3/4. I can rewrite that as 81 to the 1/4 to the negative 3. 81 to the 1/4 asks what to the 4 gives you a 1, and what 3 is 3 to the negative 3, which we know is 127. 100 to the negative 2/5, or sorry, to the negative 2.5. That's 100 to the negative 5 over 2. Again, I can rip this exponent apart. 1/2 to the 100 to the 1/2. That's just 10. So this is 10 to the negative 5. The negative in the exponent tells me to flip the base. Keep the positive exponent. The base of 10 is really nice because all I do to evaluate it is write down a 1, and then the number 0 will be the exponent that I have. So here I have 1 over 100. Now these are similar, except the only difference is they are written with a radical sign. So question D, this is really the cube root of 125 to the negative 1. Again, it doesn't matter which way I write that because it's just a power of power and multiplying those exponents. The cube root of 125 we know is 5 because it asks what to the 5 gives you, sorry, what to the 3 gives you 125. That answer is 5. And this is just 1/5. So it's 5 to the negative 1. Here I have the square root of 4 over 49, negative 1. Well, again, we know that the square root of 4 is 2, and the square root of 49 is 7. The negative in the exponent tells me to flip the base. Question F, the cube root of 8 to the negative 5. I can rewrite that as the cube root of 8, all raised to the negative 5. And the cube root of 8 is 2. And 2 to the negative 5 is 1 over 2 to the 5, which is 1 over 32. So now we can use these, and we can use these radical signs as we solve for equations, exponential equations. So again, first of all, I know that this is an exponential equation because the unknown is in the exponent. The only way that we can do that right now is get a common base. Even though we don't know the square root of 8 or the cube root of 32, we still see that we can get common bases of base 2. So all I've done is rewritten the 8 as 2 to the 3, and 32 as 2 to the 5. I see that the square root here, so I'm going to write that as an exponent of 1/2. And see I have the cube root, that's just an exponent of 1/3. Now I have powers of powers. So I'm going to keep the base and multiply those exponents. I did that step by step here. I multiplied these exponents. And now I'll multiply these exponents. Notice on the right-hand side, in an attempt to get common bases, I had the 1 over 2 to the 5. So I flipped that and made up 2 to the negative 5. Now I can continue with my powers of powers, multiplying top by top and bottom by bottom. And now I have my bases are the same, so my exponents have to be the same. So I can set these exponents equal to each other, and I can solve for x. We multiply both sides by 2, and then subtract 12, and then divide by 3. And so had I plugged in x equals negative 5.19 into the original equation, I would have saw that the left-hand side and right-hand side give me equal numbers. Here's another example with cube root of 9 equals 27 to the 4 minus x over 6. Now again, I don't know what the cube root of it is, but I see that I have 9 and 27. That's a base of 3. I also see that the cube root is the exponent of 1/3, and so I might as well do that first. Although I could have left common basis first, it doesn't much matter. So here I'm putting in 3 squared and 3 root 3 for 9 and 27. Now I have powers of powers, so I multiply the exponents. Top by top, bottom by bottom. It's important to note here that I'm taking the 3 and multiplying by 4, and then the 3 and multiplying by the negative x. Now my bases are the same, so my exponents have to be the same, so I can write a new equation just with the exponents, and I can undo what's being done to x. Multiplying both sides by 6, then I could subtract 12 from both sides, and then divide by negative 3. So now we'll look at some patterns, and from those we'll go into the word problems again. So we saw that we have a pattern like this. There's no common difference, but because there's a common ratio, we can write it in terms of the first term in the common ratio. And so we would have 120 times 0.5 to the n minus 1. Now remember, I can't multiply the 120 with 0.5. I actually don't have 0.5 here. I have 0.5 to the n minus 1. So I don't know what that number is, so how can I multiply by 120? This isn't the only type of equation we can have. We can also have one where y equals a times common ratio to the x over the period. And that usually happens where we have to do that when the x values aren't going up by 1. And a is the initial amount, and r is what's happening to the debt, the common ratio. So for instance, a certain bacteria sets triple every 12 years. In 1950, there was 2,500 individuals. How many will there be in 2001? Now notice, right away here I see that it's every 12 years, there's the period. It's tripling, there's the common ratio, 3, and there's the initial amount. So I can get this equation. Now this is a rational exponent, by the way. That's why this is coming up again. So we're going to solve for x here, knowing that x is the number of years since 1950. And if we want to look at how many people there are, how many individuals there are in 2011, we're going to plug in x equals 60. And so we would see that there is 665,718 individuals. So if we had the same scenario, what could we could also ask? We could also ask, when will there be 67,500 individuals? And so again, we have the same equation, but now we're trying to plug in y equals 67,500. And so again, we're solving an exponential equation, the exponent has the unknown in it. And so to do so, we have to isolate the power by dividing both sides by 2,500. And look at that, it comes with a 27. Yay! Because now I can get common bases. And since my bases are the same, my exponents are the same. I multiply both sides by 12, and I get x equals 36. But x is the number of years since 1950. And so what will happen here is that we'll see in 1986 there will be that many individuals. Now, this question is just a joke. I'm not complaining about teacher salaries. And teachers make a decent wage, and yeah, it's just a joke. So a teacher's salary increases by 6% every 15 years. In 2000, starting teacher salary was $35,000. what will be in 2020. Now, this is the starting salary. It's not the salary of the teacher as they progress in their career. Let's look at this by looking at a table of values. First thing we'll do is look at X being the number of years since 2000. Because the question says that it's increasing by 6% every 15 years, we'll look at every 15 years, look at 15-year intervals. And Y will be the starting salary in thousands of dollars. So the first data point is $35,000. And so we want to figure out what this would be in 2015. So to do so, I'm going to say 6% of the 35, which is 2.1, and I'm going to add this to the 35. And so this means that in 2015, the starting salary would be $37.1 thousand. To get the next one, I'm going to take 6% of that and add it to 37.1. This gives us 39.33. And in fact, you can see that I will always do the same thing. I'm going to take 6% of this new value and add it to that value. So here's the data table, which means in 2045, a starting teacher will be making $42,000. I'm rich, yeah, well, no, but in 2045, I'm not sure what can, I don't know what you buy, probably a little Honda Civic for $42,000 probably. In any case, this is the data for this made-up question. And so if you look at the common ratio, we get 1.06. But of course we do, because we took each successive value is 1.06 higher than the x, or higher than the loss, I should say. And that's because we took 6% and added it to the original loss. So 6% of x is 0.06x. And then we take that and add it to the x value, we get 1.6x. So since we have the common ratio, we can now find the equation. Notice that we can find this common ratio very quickly, because when it says that it increases by 6% a year, we will always have 1 plus the interest rate. And 1 plus 6% gives us this 1.06. If it says depreciates, then you're talking about the common ratio is 1 minus the rate divided by 100. And so we'll just have to keep those in mind that those will come up from time to time in these questions. And this enables us to do this without using a data table. I could quickly see from this equation that since I started with 35,000 and I increased by 6% every 15 years, I can get this equation. So now I'm trying to figure out what would this be in 2020. Well, that's 20 years after we started, so I'm going to plug in x equals 20, and then use my calculator to solve. And this means that the starting teacher's salary would be $37,830, which again, you can see is the 20 kind of shows up right in here, and that's where this value shows up. So we know we have a reasonable answer. Another type of exponential question with a rational exponent is a half-life question. Half-life is involved in radioactive decay, where the process is random, but because you have billions upon billions of these radioactive nuclei, the pattern overall will happen in a predictable way. And so what happens here is that in a half-life scenario, you're left with half of the material. Okay, and so after one half-life, half the material is left. After 2 half-lives, you have a quarter of it, etc., etc. And so if we look at an example here, certain radioactive substances are half-life, I should say, sorry, of 8 days. It initially contains 90 milligrams, then there will be 5.625 milligrams left. Well, again, I can model this with an equation, and all half-life equations have a base of a half because the data is halving each time. And so I started with 90, and and the period is the half-life value. That's the 8, in this case 8 days. And so I'm going to plug in y equals 5.625. I'm going to isolate the power. I get 1/16 here. If you have to do this on your calculator, which I suspect you would, you're going to look for a button that is F to D or something like this. That's fraction to decimal. Or you might look for a button that looks like this, or B to C. So you would type in your 5.625 divided by 90, and then you would hit one of these buttons. You already hit equals, and then hit F to D. And that goes into a fraction. If you can't find that on your calculator, you could maybe take a screenshot of your calculator and send that to me, and I would be able to point out where that button is. And that is helpful because now I can see that I have 1/16, so I can get common bases. And so 1/16 is 1/2 to the 4. Since my bases are the same, my exponents are the same. And so I can see here in 32 minutes, there would be that much left. Or sorry, not minutes, days, because the half-life is in days. Here's another example of a half-life question. A certain substance has a half-life of 65 minutes. When will there be 1/64 of the original amount? And so I'm not given the original amount, so I'm just going to leave that as this A value. And so again, I see here that the period, the half-life is 65 minutes, and so there's where that goes. In this case, X is going to be measured in minutes because the half-life is. Oops. Now the original amount is, or sorry, the amount that we're looking for is 1/64 of the original amount. And so that's going to mean that I have 1/64 times A. So if I plug that into my equation and then divide both sides by A, I see that I don't need the original amount. And so I can get common bases now. And since my bases are the same, my exponents would have to be the same. And so in 390 minutes, we'd have 1/64 of the original amount left. Another type of scenario where these rational exponents come into play is a compound interest equation. Compound interest is when you get interest on your interest, the title. And so what happens is that we get a certain amount of interest in a month, let's say, and that increases your principal. And so the next month's interest will be slightly bigger because your principal is slightly bigger. And so if we looked at investing $100 in an account paying 6% interest a year compounded quarterly, we could figure out how much we'd have in 10 years. So we're going to get 6% a year, but it's going to be spread over, it's going to be done 4 times. And so we're really going to get 1.5% each time. And so that will show up in our equation. Here we have our initial amount of 100. Here's the interest rate we get, and we get this every quarter of the year. So 1 quarter is the period. Now we can simplify that exponent by flipping the multiplying, and we get 4x. Then we can plug in x equals 10, and the calculator gives us 181.4. So $181.40 is what we have. Now we can actually generalize this. P is our starting amount, R is the interest rate, N shows up twice in the equation, and it's the number of times a year compounded, and T is the number of years that we've had the money in the account. So you're looking for the word compounded to use this equation. You'll only use this equation when you see the word compounded. And you'll see things like compound daily or semi-annual, and those change the end balance. You can see that. So if I have a bank account earns interest compounded monthly, the investment doubles in 9.27 years. Calculate the interest rate. So what I see here is the doubling, but I see more importantly this word compound. So this is going to tell me to use a compound interest equation. Now I don't know what the principal value is, and I don't know what the interest rate is, but I do know that the interest is compounded monthly, so it's going to be n equals 12. And it's asking me, or tells me that it doubles in 9.27 years. So I'll put in t equals 9.27, and I'll put in 2p for a. And I'll isolate the power and simplify that exponent. And now I'm trying to solve for a base. Now we've done that at the beginning of tonight. We did that when we had x squared equals 25. And we did so by raising both sides to the reciprocal exponent. So here I'm going to do the same thing. I'm going to undo the exponent by raising both sides to like 1 over 111.25. On the right-hand side, I have a power of power, which is going to be equal to 1, and then multiply those exponents. And so now I can subtract 1 from both sides, and multiply both sides by 12, and then solve using my calculator. And so this, I think the calculator, and the calculator earns 7.5% interest compounded monthly, will double every 9.275 years. And so compound interest is very important. It's how your credit card company makes so much money. It's how you owe the credit card company so much money. And it's also how your investments work in a generalized way. So we'll look more about that next week as we will solve harder questions, ones that we can't get a common base for. Good luck with the homework. We'll talk to you next week.